Okay, go ahead. So here we go. So a computer program is essentially the collection of entities and actions on those entities. And the kinds of entities I'm talking about are things like in C, functions, objects, constants, types. In C++, we also have namespaces, templates. And in fact, if you look in the standard, there's an even larger list in the C++ standard of the sort of things. But you get the idea when I talk about an entity. And one of the essential things that you do in programs is that you write declarations for entities. And when you do that, you give the entity a name and a bunch of other attributes. Those attributes are things like type, scope, storage, duration, and linkage. And what I want to do is talk about scope, storage, duration, and linkage, and why it is that they're so jumbled together in the language, and what you can do to help clarify this. So one key point is that names don't necessarily have all the attributes. It depends on the category of the entity. So for example, an object has all of those things. It has a scope, a type, a storage duration, and a linkage. A function name has everything except it doesn't have a storage duration. There's no notion of a function occupying data storage and having a lifetime the way an object does. One of the least used categories is a label. When you write a goto statement, which I hope is very infrequently, you have to have a statement label. Statement labels don't have any of the attributes except a scope. So a declaration is a statement. There was a time way back when C was first specified, that declarations and statements were considered to be distinct things. Now a declaration is actually considered to be just another kind of statement. You can interleave them in blocks with other action statements. What is a declaration? It says basically, here's a name and a bunch of attributes for something that exists in the program, possibly here, possibly somewhere else. A definition is a declaration that not only says it exists, but here it is. All definitions are declarations, but not all declarations are definitions. So, simple example, that's a function declaration. Now, a lot of people will call that a function prototype. You'll note I'm not going to use that word other than to tell you don't use it. It actually has a different meaning than what most of you think it means. That's a function declaration. That's a function definition. The difference is the previous one didn't have a function body, this one does. And basically, the definition is whether it's a function. The functions are the easy ones to understand, but whether it's an object or a template or a class, the definition is here's everything you need to know about it in order to make this thing real. So once again, a non-defining declaration for a function says it exists but not here. The definition says it exists and here it is. And that's generally true with other things like objects. It's generally true with classes and templates as well in C++. Interestingly, there's, just like in C++, there is this notion of a pure virtual function. There's no official term for an impure virtual function. Well, similarly, with the terminology of declarations and definitions, there isn't any terminology in either C or C++ that says this is a declaration that is not a definition. So you'll notice that I have to keep repeating the awkward phrase, a non-defining declaration, because that's the best I could do. Now, another point that I think most of you know, but it is, notice that I'm emphasizing this, is compilers translate one source file at a time. You don't compile headers, you only compile sources, and you do one at a time. And when you compile it, whether it's C or C++, you're incorporating headers via include directives. And this is important. There aren't any rules. If you read both the C and the C++ standards, there aren't any rules which say explicitly these constructs have to go into headers. These constructs have to go into source files. And you'll see why that is in just a moment. But what they do is they leave it to programmers to develop a sense of how to do this. And style guidelines will try their best sometimes to give you some concrete guidance on this, but I have yet to see a set of style guidelines which is really that useful with respect to this stuff. It still comes down to there's no substitute for just understanding the problems that you face and being able to make the judgments. And it turns out that a lot of being able to make those judgments depends on understanding scope, linkage, and storage duration and how they interact. Now, as you well know, the initial phase of translation in both C and C++ is running this thing called the preprocessor. The preprocessor is what handles header file inclusion, macro substitution, conditional compilation like hash if and hash else and stuff like that. But this is the key term, translation unit. Just out of curiosity, how many of you are already familiar with this term, translation unit? Okay, this is a major insight. If you read the standard, you will see that, in fact, this term is used considerably more than the terms header files and source files. And that a way to picture what's happening is that the compiler, whether it's C or C++, takes your source file, and the first thing it does is it runs it through that portion of the compiler known as the preprocessor. And you can think of it as if the preprocessor is a separate program, which spits out another source file. And that source file has a name. It's called a translation unit. Essentially, a translation unit is the result of running a C or C++ source file through the preprocessor and spitting out a new source file in which all of the preprocessor directives have been processed. All the includes have been done, all the conditional ifs and elses have been handled. And now, in fact, most compilers, commercially available compilers, have compile options to say preprocess only. If you want to debug a macro, you want to check that your conditionals are being handled properly, you can actually say, give me a intermediate source file, preprocess only. And often the extension that you see on that file is .i or .ii. And in fact, most C and C++ compilers will accept one of those source files as the input. You can actually say, here's a file that has already been preprocessed, and the compiler knows what to do with it. It knows not to preprocess it any further and just run it through the rest of the compiler. And so the reason why translation units are so important is because many of the semantic rules regarding things like linkage and storage duration are not expressed in terms of headers and source files, but they're expressed in terms of translation units. Some of you may be familiar with C++ has this famous rule known as the ODR, the one definition rule. And that stuff's all expressed in terms of translation units, not in terms of headers and source files. But it still comes back that your understanding about what's going on affects what you decide to put into a header and what you decide to put into a source file. And again, most of the insights come from understanding the difference between a declaration and a definition, a non-defining declaration and a defining declaration, linkage and storage duration. And that's where we're headed. So with that little recap, oh, there's one other thing I want to talk about, which is that the compiler transforms each translation unit into an object file, also known as an object module. And then it takes a collection of object files along with possibly previously compiled object files, maybe in the form of libraries, links them together and produces an executable. Now, an executable program, most compilers have the option of producing executables which are release builds or debug builds. And I'm going to focus most of my attention on the release ones. The debug builds are essentially release builds with a whole bunch of extra stuff thrown in for debugging purposes. I'm just going to focus on the release build properties. So what's in a typical object file of a release build? Well, there's two main pieces. Now, I'm painting in broad strokes here. The details, of course, are a little bit more intricate than this. But for the most part, what you see in an object file, the information content falls into two broad categories, data and metadata. What's the data? Well, the data is things like machine instructions, turning your assignment statements into moves, loads, and stores, and your comparisons into comparisons, your if equal or while not equal loops into compares and branches. That's the machine instructions part. And then there can be values. Anytime you define storage, for example, a brace initialized array, that's going to become data that goes into the object file. The metadata falls into two broad categories. And that is, and this is key right now. We're going to really build on this part right here, which is that function names and object names can wind up as metadata in the object files. Now, what do I mean by metadata? It's that, remember, what the linker is going to do is take a bunch of these object files and try to weave them together to produce an executable, which is then a bunch of ones and zeros which get loaded into memory to execute. By the time it gets loaded into memory, things even like function names and the names of data objects are gone. It's just a bunch of machine instructions and bit patterns for data. But the linker has to use this stuff in order to be able to take two object modules in which there's compiled code, for example, for a function code call over here, calling a function that's actually defined over there. Somehow or another, the linker needs that information. And so the function and object names are often known as defs and refs. They are the definitions of things like functions and objects, and they are references to things like functions and objects. And the linker's job is to make them talk to each other. And once it figures out numerically where those addresses are, it says, I don't need that information, and throws it away. It doesn't wind up in the executable itself. There's also stuff that guides the linking, program section names. It's very common that code will be collected together into one logical section, so that if you have code in one object file and code in another object file, in the bound program they will become physically contiguous. And similarly, data in one object file and data in another will be woven together by the linker so that data will be physically contiguous, often. And that's done through the notion of logical sections. But for our discussion, that part of the metadata isn't that important. Okay, so now let's talk for a moment about scope. So remember, I said I was going to talk about three attributes: scope, storage duration, and linkage. A fundamental activity within the compiler is, as it sees declarations, the declarations have attributes associated with them. And that attribute information is important for two things. One is it's the information the compiler uses to validate, is the name being used correctly when it's being used in a context? And the other part of the attribute is, and what do I do to generate code for it? So the declarations, the primary effect of a declaration is to take information and put it into this internal structure known as a symbol table. When the compiler later sees a use of that name in the same translation unit, it will look it up and find out, is the name declared? What are the attributes? Is this use of the name consistent with the prior declaration? Or is there a conflict between this use and the attributes that would provoke a compiler complaint? And so the names are distributed into regions called scope. And essentially, your informal understanding is scope is a curly bracketed region of text. It's not exactly that, but that's most of us get by with that informal understanding. In C, there are two kinds of scope regions. There's four of them, but the other corner cases are not even worth wasting any time on. There's block scope and there's file scope. And basically, block scope is a curly bracketed block, with the exception that when you're dealing with functions, block scope includes names in the parameter list of a function definition. They are considered to be at the same scope level as local variables at the outermost block in a function, which is why you can't name a local variable the same as a parameter. And then there's file scope, which is anything that isn't block scope, anything outside of a function, structure, or union. Interestingly, how many of you program in C? Anybody? Oh, fair number of you. Very interesting phenomenon. This is, again, language lawyering, which is not worth laboring over a lot. But C does not have the notion of structure scope. We often think of the names in a structure as being in their own scope. But that is not the formalism that you see when you read the C standard. They actually say that each structure forms its own namespace, which is an alternate phrasing. But the net effect is that structure scope in, structure namespaces in C are almost the same in behavior as if they were their own scope. But like, for example, one of the curious things about the structure namespace in C is that you cannot declare things like types in a structure. Well, you know what happens if you do that? Does anyone know? If you actually put a type def or an enumeration definition inside the curly braces of a struct, do you know what happens? See, C programmers don't even go there. You do this all the time in C++. But in C, all it does is it takes that definition and treats it as if it were in the enclosing scope of the structure definition. In other words, you try to put it there and immediately it just gets dragged out one level. Structures are not their own scope in C. That's why I don't bring that up here. In C++, what C calls block scope and file scope is actually called global and local scope in C++. And I believe these are more popular terms. Even C programmers will use these terms in preference to file scope and block scope. And so that's the way I'm going to do it. Since I'm trying to talk about both C and C++, here I'm going to use the C++ terminology. C++ adds class scope and namespace scope with these interesting notes. First of all, in C++, classes, structures, and unions are all the same thing. A struct is just a class in which all of the members are public by default. And a union is just a struct in which all the members are at offset 0. But otherwise, they behave according to the same rules. And in C++, namespace scope is a generalization of the global scope. That essentially the global scope in C++ is just treated as another namespace. And you will see examples of that very shortly. But there's enough similarities between what's going on with namespace scope in C++ and the global scope in C. I can talk about them as if they're all behaving according to consistent rules. Okay, now here's a biggie. This is one of the key points of this talk. Everything else was leading up to that, which is that the concept of scope applies only to a single translation unit, one translation unit at a time. There is no such thing as global scope, which somehow escapes a translation unit into the program at large. Okay, that's the myth that I see in a lot of articles and just, online discussions about C and C++. Is they talk as if there is something beyond the scope of a single translation unit, and there isn't. Because a scope is just a region of text in a translation unit, in a source and a header file. That's all it is. There's nothing higher than that. So how is it that a name used in one translation unit can refer to the name with the same spelling in another translation unit? And the answer is, it does it with linkage. And so I want to make these distinctions really clear as to what's going on and give you what I think is a fairly accurate conceptual model of how this happens within the compiler and how it affects the way you organize things. So once again, the problem is a lot of programmers have trouble separating scope, storage, duration, and linkage, and that's because the language tries to get by. Both C and C++ do this with probably, arguably, too few keywords. In particular, the keyword static has been stretched to the breaking point in C++. And I'll show you what I mean by that. So from a language perspective, this is largely driven by these keywords in the language known as storage class specifiers. If auto, extern, register, static, thread local, and typedef. That's the current set in C. Now, a couple of things to note. One of them is thread local is actually not a keyword. And tomorrow I'm going to be giving a talk called New Features in C, and I'm going to explain the underlying philosophy of why C does what I'm showing you here is, but actually the keyword is _T, thread local. That's the reserved word. Thread local itself, with the lowercase t, no leading underscore, is actually a macro. And you can only use it by including a header first. Typedef is not really a storage class either. The grammar of the C language throws typedef in with these others simply as a syntactic convenience. And there's actually a footnote in the standard that says that. This is it's a grammatical hack. They don't use that term, just to make the grammar a little bit easier to write. But typedef is not a storage class, really. C++ provides these four: extern, mutable, static, and thread local. There is some overlap. Mutable is used only in the declaration of class members, and it's a way of essentially nullifying constness. And it's put in with the storage classes, but it's arguable that it doesn't really behave like the other storage classes in the way that I'm about to show you. What happened to auto? That was back there in the list from C. Auto has been a storage class specifier in C since C was C back in 1972. And nobody uses it. And that's because the only valid place for using the keyword auto in C is to declare a local variable. And the default, if you don't put the auto there, is auto. In other words, so auto is a keyword whose only use is to restate a default and do nothing else. It's pretty useless. So C++ said, well, since it's so useless, we have a need for a keyword, and we don't want to invent a new one. They actually stole it in C++ and made it a type specifier. How about register? What happened to that? Register is still a keyword in C, and but it says the meaning is, it says it's implementation defined, meaning it's up to what the compiler wants to do with it, and there's a footnote that says, and the intent is it's supposed to speed things up in some way. Well, in C++, the attitude is, hey, come on, optimizers do better than you can. And so it's been that way for at least 20 years now that C++ compilers have been ignoring the keyword register. And so now the status of register in C++ is it's still a keyword and it has no meaning. That's simply, they say, it's a keyword with no meaning. It will be repurposed sometime in the next decade. That's what's going to happen with it. I believe the only difference in C with register is there may be some subtleties about you can't take the address of a register object. But other than that, it behaves just like an auto. So let's focus our attention on these three. These are the three that are common to C and C++. And they're sufficient to create enough examples to show the distinction between linkage, storage, duration. Now, the rule is at most one storage class specifier can appear on a declaration, with one exception, and that exception is thread local is allowed to appear with extern or static. So you can have extern thread local or static thread local. But otherwise, you can only have one of these. And there are some declarations where this stuff just isn't permitted at all. For example, you're not allowed to use the keyword extern in either C or C++ to declare the member of a struct or a class. That's not valid. Now, there are contexts in which the presence or absence of a particular keyword has no effect. Right there. Those two are the same thing. Add or remove that extern, the program's behavior doesn't change at all. And this is true for both C and C++. In both cases, that is defining an object named n, whose initial value is 42. And if this appears at global scope, or namespace scope in C++, they behave exactly the same. On the other hand, most of the time when you do put a storage class specifier on a declaration, expect it to have an effect. In particular, with those two at the bottom, the first one has the explicit presence of extern. That turns that declaration into a non-defining declaration. It says this is not a definition for n. This is saying there is an n and it's somewhere else. But the second one says there's an n and here it is. And again, this is true in both C and C++. When this appears at non-class scope. So what's the underlying principle behind that distinction between extern or no extern? It's that for objects, see with functions we saw earlier the distinction between a declaration that's not a definition and a definition is the presence or absence of a function body. With objects, there isn't a simple syntactic specification that says this one is a declaration, not quite as clear as that, but as you'll see in a moment, it's almost as clear. But the underlying concept is that an object definition is going to allocate storage, and a non-defining declaration is not. It's going to say it's somewhere else. So the C++ rule for definitions outside of a class is right there in bold. It says that a declaration is a definition unless it has the keyword extern and no initializer. So that first one lacks an extern. Notice it doesn't have initializer, int I, but it also lacks extern. That's a definition. That allocates storage for I. What's its initial value? Anyone know? What's the initial value? Pardon? Yes, if it occurs outside of a block, it's actually defined behavior that it's 0. And that's just not a quirk of some compiler. That is a specification of both the C and the C++ standards that statically, it's actually, I just jumped ahead. It has the property that that thing is statically allocated, which I'll get to in a moment. Statically allocated objects are zeroed at program startup. And that is a well-specified feature. Now for local variables, that's why you were hesitating. Local variables, the official term is it has an indeterminate value, which is a polite way of saying it's whatever stray bits were in there from some previous use of that storage. The second one of these, extern int j, that's the way you write a declaration for an object in C++ to guarantee that it's just a declaration. And then the last one is a definition because although it has extern, it has an initializer, which says, hey, I can't put an initial value there unless I'm also allocating the storage. So what are the implications of this? Well, if you want to, what you'll see in a moment is that there are real problems putting the first one or the last one in a header file. Only the one in the middle can safely be placed in header files in general. Now, the rules in C are a bit more complicated than this, but if you follow this C++ rule, it will work perfectly in C. Okay, C has some more intricate wording that allows a little bit more slop, and I just encourage people, just follow the C++ rules, whether you're in C++ or C, and you won't go wrong. You will not have conflicts. Now, here's what makes static particularly troublesome. One is that sometimes it affects the way programs allocate storage. Other times it affects the way object files link together. And then in C++, it turns out it can alter the behavior of a class member function. That the keyword static doesn't change the storage allocation, it doesn't change the linkage properties, it only changes the parameter list of a function in a subtle way. So remember this about class storage specifiers, which is that they affect linkage and storage duration of names, but they don't affect scope. So what I've used this term storage duration. Now let's dive in, talk about a little bit about what it is. It's that it affects the lifetime of an object. It's how does the runtime system of a program manage the storage for an object. By the way, this is a property only of objects, not of functions, not of data types, but of objects. And the four kinds of storage duration are static, thread, automatic, and dynamic. Thread is relatively new. That was added in C++ 11 and in C 11. So what does static storage mean? It means basically the storage for the object is allocated when the program starts. And the object stays where it is in place for the entire execution of the program, and it goes away. Well, after the program's done running, you don't care whether it goes away or not. Thread storage duration there's a real similarity between that and static. The only difference is that it's the duration of the execution of a thread. Thread starts up. If it has thread local storage, that thread local storage will be allocated at that time. It may have been set aside prior to the start of the thread. Conceptually, you only have access to it until the thread starts running. And it's there as long as the thread remains running. Automatic. This is the stuff that's typically local to a block, right? Inside a curly bracketed function body or a block nested therein. And the storage is allocated when the block begins. Now, just a brief aside is that functions can have blocks within them, and there can be declarations within those curly bracketed bodies. Does the runtime system wait until it enters a block to actually allocate that storage, or is it allowed to do it earlier? And a lot of compilers will actually look at all the nested blocks and figure out how much storage do I need for the most deeply nested, for the outermost block and the most deeply nested one, and it will allocate all of that upon function entry. And it may be that some of that stuff in the stack doesn't get used. But the concept is, though, that storage isn't allocated until you actually cross over the curly bracketed body and enter that block. And conceptually, it goes away when you exit that block. But it may be that it waits until it actually returns from the function to actually deallocate it from the stack, because that's often more efficient from a performance standpoint. Dynamic, this is the stuff that you do manually. In C, it would be commonly with malloc, calloc, realloc, functions like that, and free. In C++, it's typically operator new and operator delete, and there are lots of different flavors of operator new and delete within C++, but it's a manual operation. And you're carving up a pool of memory, often known as, in C, it's called the heap. In C++, it's called the free store. And now linkage. This is the most interesting one. Essentially, linkage is the property that a name can have, which allows a name to be declared in more than one place and have those two declarations wind up referring to the same entity. That's what linkage is. And there are three kinds of linkage: external, internal, and no linkage. We're going to go through each of these in some detail. And then drum roll, turns out C++ is going to add, it's now in the new specification of C++, C++20 has a feature called modules. And modules, the intent is to eventually replace the use of header files with a different scheme for doing separate compilation that frees us from some of the tyranny of the preprocessor. And so in order to support the semantics of modules, there's now another kind of linkage called module linkage. Now, modules are a whole nother lecture. So other than to mention that this is coming down the road, I'm going to stick with the other three. That'll take up the available time we have anyway. But one of the things that I want to suggest is that those of you who are going to be working in C++, what you want to do as you tackle your new understanding of modules is apply the kind of stuff that I'm talking about here as make sure that you have a good underlying model of what modules are doing in terms of storage duration and linkage, because that's where the key insights are going to be. You're going to see a lot of tutorials that'll just say, don't worry, just do this, and it'll work. And there's a lot of that goes on in C and C++. And for the most part, people learn to program in C by not worrying about it until it bites them, right? And then you got to really figure out what's going on here. And this is the model, the kind of model you need. Okay, so external linkage is when you can have a name declared in two completely separate translation units. The same name, but at link time, those two names become one. So the external that's the way you cross one translation unit boundary to another. This is what's really happening when people tell you that when you put the word static, it takes it from being this super global scope down to just being a module level scope. Well, they're really trying to avoid telling you that the real machinery that does this is external linkage. That's really what's going on. And so here we have a total, an object called total, which is defined in file 1. But notice it's got the keyword extern on, which says it has external linkage. But that is a definition. It does have an initial value equals 0. In the second translation unit, file 2, it says extern in total. That does not have an initializer, so that's just a non-defining declaration. Those two things become one. After separately compiling each of those, you link them together. There's only one total in this program. Compare that with internal linkage. Names with internal linkage can be declared multiple times within a single translation unit, and they all wind up referring to the same thing. But they can't but nobody outside the translation unit can refer to those things with internal linkage. So here in file 1, we have total now declared with the keyword static. That's not just a declaration, that's a definition for total with internal linkage. And in the other file, you have a non-defining declaration with external linkage. And that says, hey, I don't have any storage. I need it from somewhere else, but it can't get it from file 1. File 1 does not have external linkage. These things, the linker can't make them become one. So if you want this by the way, if you try to build this program, because that's an unsatisfied reference in file 2, you would probably get a link error. At link time, it would say, I don't see a definition for total to satisfy that. And you say, well, can it get out of file 1? The answer is no, because file 1 does not. That total does not have external linkage. So what you need is a third one there. You need to have file 3 has a definition for a total so that the one in file 2 can refer to the one in file 3. Now the program will build. And how many totals are there in this program? There are 2 of them. One internal to file 1 and one that's shared by file 2 and file 3, shared via external linkage. Then there's the concept of no linkage. Local variables have no linkage. You have 2 functions, f and g. They each have a local variable named total. But think about it. Is there any way you can write a declaration for total anywhere else in the program that will, at link time, become a reference to one of those totals that's inside the function body? No. See, those totals have automatic storage. They are not statically allocated. Because they don't have a fixed location, there's no way that the linker can say, oh, I know how to link to that thing, because that thing doesn't have a guaranteed spot at runtime. The only things that can have linkage are things that have fixed locations. Functions and objects with static storage. So here's a good conceptual model of what's happening, is that names that have external linkage are names that are passed on to the linker in a release build. Names that have internal linkage and no linkage are useful if you're doing symbolic debugging, but the linker doesn't use them when it is combining object files together to produce an executable. So names defined with external linkage in a translation unit become defs, definitions in the compiled object file. Names declared with external linkage but not defined become refs. Essentially, a def in an object file says, I've got an externally defined name and I'm making it available for other people to refer to it. A ref says, my translation unit needs this thing. I'm mentioning this name, but I don't have a definition for it. I need to get it from somewhere else. Those things are passed on into the object files if they have external linkage. And for the most part, the compiler discards names that are declared with internal or no linkage. They don't make their way into the release build object files. Okay, so let's look at some examples here. By default, functions which are at file scope in C have external linkage by default. Right? So most of the behaviors you're about to see are things you're going to nod. Yeah, I see this, and this model that you're giving me fits. But I think it's worth illustrating them with a few examples. The same thing will happen if you put names at namespace scope in C++. Adding the word extern on a function declaration has no effect. For a function that's at global scope or in a namespace in C++, whether you put the extern there or not, the behavior is the same. Class members in C++ have external linkage by default. Those of you who do program in C++ know that you commonly place class definitions in header files. And you include those all over the place and create objects of that type and call member functions on them. And at nowhere did you say these things were extern. You just treat them as if they are. They have external linkage by default. And if you explicitly put the word extern there, the compiler says, no, I got it covered. You have no choice about it. It's extern. So you can't even restate the default in C++. Now, when you declare a function with the keyword static, all that does is change the linkage. Functions don't have a storage duration, so the only thing that this is doing is changing the linkage properties. Gives it internal linkage. But with C++ classes, there are these things called static member functions. And as I stated a moment ago, class members in C++ always have external linkage, and this static doesn't change that. Even these things called static member functions still have external linkage. What happens is it changes the parameter list. In C++, class member functions have an implicitly generated parameter called this. And what the keyword static does on a function is it tells to the compiler, take away the this pointer from this function. Which seems like, what? Static does that? It turns out it's actually because that makes sense given what a static data member is. That static member functions are used for manipulating static data members, and static data members turn out that's not such an outrageous thing to call them that in C++. Now, objects at file or namespace scope always have static storage duration. It doesn't matter what keyword you put in front of them. If it's global or if it's in a namespace, they always have static storage duration. What does the static or extern do? It changes the linkage. So let me just, as an aside here, the key point I'm trying to make is the real insight into what's going on in C and C++ with respect to objects and functions is to understand there are these three attributes: scope, storage duration, and linkage. And the keywords can really lead you astray, because if you're talking to somebody else and you just say, I have a static object here, what does that really mean? Are you talking about something with static storage? Are you talking about something with external linkage and static storage? Or are you talking about something with internal linkage? The way to clarify your conversations with your colleagues is to use the underlying attribute when you talk about the property of the thing, and then understand that the way it got there was through the appropriate use of the keywords extern and static and the proper placement and scope. Objects at local scope can have almost any storage duration as well, in that notice that the first one has static and the second one are both static storage duration. The third one has auto storage duration. Notice that question mark behind the word external there, because extern actually has a curious behavior, which is extern doesn't always mean external linkage. And let me show you the example here, which is that the actual rule in both C and C++, one which you should not, I'm showing you this more for entertainment value than anything else. I would not take advantage of this very much in your programming. But a name declared extern has internal linkage if it was previously declared in the translation unit with internal linkage. The illustration here is, notice I have foo is defined to be, or declared to be, a function with internal linkage in this translation unit. And then I come down into main and I say extern int foo. And that extern doesn't give it external linkage. It looks and says, oh, you previously had internal linkage. You still have internal linkage. Now, declaring functions locally like that, that's a leftover from C, which most of us don't do anymore, right? But it turns out that when you read the standard to find out what extern mean, it doesn't just say external linkage full stop. There's this extra verbiage for a feature you don't want. But here's a couple other things. Linkage also explains a subtle behavioral difference in a couple ways with const objects. As you well know, the traditional way in C of handling symbolic constants is to use macros. This is discouraged very much in C++ because they don't observe the scope rules. Macros, because they're handled by the preprocessor, and the preprocessor doesn't know anything. The preprocessor thinks a curly brace is just an interesting looking character. It has no semantic value to the preprocessor. And so, whereas with other kinds of entities, you can have things local to a function, where in C++ you can put them in namespaces or classes. You can't do that with a macro. And so C++ looked for ways to avoid using macros for this purpose and came up with using constant objects. Now these things exist not only in C++, but they were actually in C as well. The history, by the way, is that they started out in C++, and then they got brought over into C. And this C committee decided, for whatever reasons, to change the semantics so that they don't quite work the same in both languages. And it turns out linkage is part of the difference. And so I'll just show you. So anyway, you can have constant objects of an integer type, of a floating type, of a pointer type, and they observe the scope rules. Here's the key thing, is that there's this concept in both C and C++ of what's called a constant expression. Constant expressions appear in a number of places, like, for example, when you specify a bit field. The width of a bit field has to be, it can be a symbolic constant, but it has to be a constant whose value is known at compile time. And that code right there compiles in C++, but not C. Because the C compiler does not regard max there as a symbolic constant whose value is known at compile time. It says, this is an object which happens to have a 16 in it, but I have to act as if I don't know that the value is always 16. Which makes symbolic constants in C considerably less useful than they are in C++. And so the difference is that in C, they have external linkage by default. So if you were to do this, where you put a symbolic constant in one source file and in another like that, you'd actually get link errors. That code will compile both translation units and then fail at link time because the symbol sum is multiply defined. But in C++, in order to make it convenient to use these things as symbolic constants, they said, okay, we're going to give these things internal linkage. Const objects have internal linkage by default in C++, so that you can just have a symbolic constant and have its value known. And you can also know that nobody in another translation unit is linking to it to screw up the known value at compile time. And so this makes it feasible to do this. To take, this is the common thing, is to be able to take a symbolic constant definition like that, put it in a header file, and include it in multiple translation units, which is the way you'd like to treat a symbolic constant. And it works in C++ because when you include the header in each of those places, sum has internal linkage. Each translation unit has its own copy that nobody else can see. Now, in this case, they all have a copy of something with the same value, which is very useful. But the compiler can do all kinds of nice compile time analysis on it that it can't do as easily in C, because the linkage gets in the way. So the problem is that if you take this same code and compile it as, oops, my battery died. Here, can I use the cursor key here? Is there, on this unit, that you covered up the cursor keys, what should I use? Page up and page down, or? Use that? Okay. Oh. Oh, okay. It wasn't my clicker. Something happened. Did timeout? Okay, anyway. So there, that's what happened was, if you do this in C, then that thing with internal linkage up there becomes external linkage. Now you get the same name with external linkage in both translation units, and it doesn't build. Last thing, inline functions. What's the behavior of those? Well, how many here, you familiar with inlines? Okay. Yeah, inlining says what I'd like the compiler to do is substitute the body of the function at the point of the call. But it's not a guarantee. This substituting the body of the function at the point of the call is the desired behavior, but not a guarantee. That it is possible that the compiler will decide, for various reasons, I'm going to translate it into a non-inline call. And so what happens then, so the consequence is, by the way, that with normal non-inline functions, you declare them in a header and define them in a C or CPP file. But with inline functions, you actually put the entire function definition in the header. That's so that the function definition is visible at the point of the call. And then the problem is that's now a definition of a function with external linkage. If it's not inlined, you're going to have multiply defined symbols. But if it's inlined, it's okay. And now, but what happens if the compiler says, but I'm not going to inline it? Because inlining is only a request, it's not a mandate. What will happen is the compiler will compile non-inline calls into calls with external linkage. And it will then say the copy that I generate of the non-inline function, there will only be one and everybody goes to the same spot. So when they talk about inline functions having linkage, if it's always inlined, there's never a function to jump to. But when it's not inlined, you're guaranteed there's one and only one copy. And linkage, again, is a key part of that explanation. Okay, so that's it. In summary, here are the key points. Is the storage class specifiers, extern and static, don't affect scope. They affect these other properties called storage, duration, and linkage, or in C++, they can affect a parameter list of a static member function. The scope, the concept of scope is only meaningful in a single translation unit. There's no scope beyond a single translation unit. And the key thing that allows two translation units to communicate with each other is that the names in them have external linkage. And if you remember those key points, most of the rest of this stuff makes an awful lot more sense. I hope that was helpful. Thanks very much for being here.